In section 10.3, we're going to be exploring more things about the properties of chords. So just as a reminder, a chord is a segment whose endpoints are on a circle. Therefore, any chord divides the circle into two arcs, just like in this diagram. So if you have a chord right here, it's dividing it into the blue arc, which is a major arc, and the smaller red arc, which is a minor arc. A diameter, which remember is a chord that goes through the center of the circle, divides the circle into two semicircles. Any other chord divides the circle into a minor arc and a major arc, just like we discussed before. So again, a diameter cuts a circle into two semicircles, so half of a circle. And again, just any chord that's not a diameter cuts it into a minor arc and a major arc. Next, we have a theorem, theorem 10.3. In the same circle or in congruent circles. Remember, that just means that the radius has to be the same. Two minor arcs are congruent if and only if their corresponding chords are congruent. So since this is an if and only if statement, we can do this forwards and backwards. So if we know that AB, arc AB, is congruent to arc CD, then we would know that chord AB is congruent to chord BC. We also know it the other way around. If you know that these two chords are congruent, then their arcs would be congruent. So let's put that theorem to use. Here's example number 1. In circle R, segments AB and CD are congruent, and the measure of arc AB is 108, which is shown in the diagram. Find the measure of arc CD. So since we know that the chords are congruent, then we know that their corresponding arcs are going to be congruent. So if we know that arc AB is 108 degrees, then arc CD is 108 degrees. Next, we have some more terminology. Bisecting arcs. If arc XY and arc YZ are congruent, just like in the picture, then the point Y that they have in common, and any line, segment, or ray that contains Y, so in this case this would be segment YC or CY, bisects the arc XYZ. So again, if these two arcs are congruent, that means that this segment is bisecting the big arc XYZ. Next, we have two more theorems, theorem 10.4 and 10.5. So first, let's look at 10.4. If one chord is a perpendicular bisector of another chord. So looking at the diagram, we see that this chord SQ is not only bisecting chord RT, but it's also perpendicular to chord RT. Then the first chord is a diameter. So as long as this bigger chord is bisecting and perpendicular to another chord, then you know that that first chord is a diameter. Theorem 10.5. If a diameter of a circle is perpendicular to a chord, so again we see that this is a diameter because it's going through the center and it's perpendicular to this chord FD, then the diameter bisects the chord, so we would know that the chord is being bisected, so FH and HD would be congruent, and it also bisects the arc, so we would know that arc FG would be congruent to arc DG. So here's example number 2. Use the diagram circle C to find the length of segment BF. Tell what theorem you used. So first I noticed that I have a diameter. Here AG is a diameter since it's a chord that goes through the center. I also see that it is perpendicular to chord DB. According to that last theorem, 10.5, if I have a diameter that is perpendicular to another chord, then it is not only bisecting the chord, but it is also bisecting the arc. So if it's 10 over here, it's going to be 10 over here, and that's the length that we're supposed to find. So the length of BF would be 10. And we used theorem 10.5. Our last theorem of this section is theorem 10.6. It states in the same circle or in congruent circles. Remember, that just means that the circles have to have the same radius. Two chords are congruent if and only if they are equidistant from the center. So again, we're using the phrase if and only if, so we know that it's true forwards and backwards. So to start, if I know that chord AB is congruent to chord CD, then I know that the distance from the chord to the center is equidistant to the center of the circle. And remember, if I'm talking about the distance from a line or a segment to a point, it has to be the perpendicular distance. So once again, if AB and CD are congruent, then I know that the distance from E to F and E to G is congruent as long as it's perpendicular. I also know it the other way around. If I know that these two segments are congruent, then I can conclude that the chords are going to be congruent. We'll see this theorem put to use in the next example. So here's example number 3. In the diagram of circle P, PV and PW are congruent, and we're shown that by marking of the 2 tick marks. QR is 2x plus 6, and ST is 3x minus 1. They want us to find QR. So using that last theorem, we know that if 2 chords are equidistant to the center of the circle, and again, it's important that we see that it's perpendicular. If those perpendicular symbols weren't there, we could not use that theorem. But again, according to that last theorem, if 2 chords are equidistant to the center of the circle, then I know that QR and ST are congruent. So in order to find the length of QR, I'd have to find X first. So what I'll do is set QR equal to ST. So again, I will take the 2x plus 6, which QR is equal to, and set it equal to ST, which is the 3x minus 1. So now I just need to solve for X. So I'll subtract 2x from both sides. So I'd get 6 equals X minus 1. Add 1 to both sides, so you get X equals 7. But remember, I'm trying to find the length of QR. So now that I know that X equals 7, I'm just going to take the 7 and plug it back in for what we know QR is equal to. So QR is equal to the 2x plus 6, so it'd be 2 times 7 plus 6. 2 times 7 is 14, plus 6 is 20. So QR is 20, which we would also know then that ST is 20 since we know the 2 chords are congruent. That's it for this section. Make sure you jot down anything you didn't understand that we can go over in class before we move on, and we'll see you then.